Yeah, so so this talk is going to be about periodic behaviors and graceful transitions between them for bimodal systems. Uh, so the system that we will consider in this talk is a 1D jumper on a spring-like terrain. The motivation for considering this system is to understand the dynamics of jumping on deformable terrain such as granular media or a trampoline-like terrain. A lot of the work in the bipedal robotics or in the Lego robotics community focuses on locomotion on flat ground, but or uneven terrain. But we want to focus more on in this talk on materials like sand or deformable terrain like a trampoline, etc. So, and as for first step, we consider this simple 1D system to try to understand the behavior. So this is the system. We have a mass M. This is that represents the jumper, and then the trampoline represents the blue mass capital M, and with a spring, of course. And we want to analyze the periodic orbits of the system and how to gracefully transition between them. So we propose a method to gracefully transition between the different periodic orbits in this talk. So the dynamics are as follows. So in mode 1, the two masses are together as a single mass, and the dynamics is just given by Newton's laws as follows. So we can calculate what the acceleration is, and the masses are together whenever the normal force is positive. That is whenever the x position is less than or equal to 0. And in the mode 2, which is the flight phase, the masses are apart, and we have and the jumper has ballistic dynamics, and the trampoline has its own independent dynamics. And the combined velocity post impact can be calculated through conservation of momentum. And the control input to this system is basically an impulsive kick that can be applied whenever the two masses are together. So in the ground phase, the jumper can decide when to kick, and he can also determine what the impulsive strength should be. So our criterion for finding periodic orbits is basically an energy condition. And essentially, when the impulse is applied by the jumper, so when the jumper kicks, energy is injected into the system, and then a flight phase ensues. And when when the red mass in the figure again hits the blue mass, ground phase, they then transit to the ground phase. But in doing so, energy is lost due to impact from the collisions. So for finding periodic orbits, we just need to, for this simple case, make sure that the energy is conserved, i.e. the energy that is injected into the system during impulses is lost, exactly lost due to impact. And we can actually compute explicitly what the energy should be. So these are some of the equations for that, expressions for that. And so this is the energy that is gained from when we transit from ground phase to flight phase. And this is the energy that is lost due to impact, which is negative. So here the energy is positive and here the energy is negative. And for periodicity, we need this to be exactly equal to 0. And we can use this. So this is some of the expressions for what the jumper solution in flight phase would be, the jumper and the trampoline. And we can essentially solve for the impulse P such that the net energy is equal to 0 numerically. So once we do that, we get, so actually it turns out that for this, there can be multiple values of P satisfying this, as we show here. So for example, this is for one value of P, This is for a slightly larger value of P, and uh, yeah. So I actually, so sorry, this is the so the here um, there's also um, the position where the impulse is applied, and these plots show where the impulse is applied. So the same impulse is applied, but at different depressions or positions along the trajectory, along the ground phase, and these show a plot of these different periodic orbits. Uh, and we also have a so-called timing diagram. So for a fixed x and v, there can be multiple p's that satisfy this delta E net of p equal to 0. This gives rise to different periodic orbits. So to give an example, it would be something like this. So we have like a periodic orbit for this, and then for a slightly larger impulse, there is a much larger ballistic impulse, and so this is type 1, and then there's type 2, and then there's type 3, and so on. So the larger values of impulses give rise to longer periodic orbits and with much larger flight phase. So uh, we can actually plot this in terms of a timing diagram. So for x versus impulses, this is what we would get for different periodic orbits. So this is for a type 0 orbit, we can get a timing diagram. Um, yeah, and so for higher orbits, this is how the timing diagram would be. So there would be a type 1, and then there would be a type 2 periodic orbit. So for a higher timing diagram. Uh, so with the timing diagram, we can obtain Raccordations. So to do that, we just divide the x min x max into equal increments and use this graph or this table to determine what the corresponding impulse should be at the ith step. So for example, this is how it would look for like this is between a periodic orbit with a very small impulse and along the timing diagram, and this is where we actually decide to leave much earlier. So here we are leaving much later, and here we are leaving much earlier in the ground phase. And by looking at the timing diagram, we can determine what the impulse should be at the ith step, and this is how the resulting trajectory looks like. This is for a periodic orbit with energy, with periodic orbits of fixed energy of a fixed ground phase energy of negative 300 joules, and this is on the other side is for negative 100 joules. But if you want to make a accordation between different orbits of different types and energy, then we would have to the alternative method that we propose here is basically to formulate and solve an optimization problem. So in this, we essentially we want to transition gracefully between different periodic orbits. So the cost that we minimize is essentially the strength of the impulse minus the previously applied impulse. So we want to change our impulsive strength as gradually as possible, and similarly the position where the impulse is applied, we would want like that also to change as gradually as possible to try to get a graceful transition. And these are just the dynamical constraints. Since the dynamics was pretty simple, we could actually integrate it out and express it in this form. So this is relates to the impact dynamics. This is just the ground phase dynamics, the flight phase dynamics integrated out, and this is the ground phase dynamics that is also integrated out. And ultimately, we can express this as a nonlinear program subject to these constraints, and we can use MATLAB's fminCon, for example, to solve this numerically. And so this is again from type 0 to type 0, we can get like a set of Raccordations in this form. And so for type 0 to type 1, this is how it looks when we solve the optimization problem. This is the plot of some of the impulses. This is the plot of the energy, ground phase energy at the end of each cycle. And this is the plot of the position at which the impulse is applied. And this is type 0 to type 2. And yeah, again, this is energy, impulse, and position. And this is type 0 to type 3. Yeah, so in this, we essentially describe the equations for a 1D jumper on a trampoline, gave necessary and sufficient conditions for finding periodic orbits, used this to solve for periodic orbits. The timing diagram introduced to show the variation of the orbit with respect to departure position. We distinguished between different types of periodic orbits and optimization problem, posed and solved to obtain graceful transitions between the different orbits.